Welcome! In this session, we'll dive into LeetCode problem number 1203, sort items by groups respecting dependencies. This problem challenges us to handle dependencies both within and between groups of items. It's a fascinating problem that combines graph theory and topological sorting concepts. Let's explore how to approach and solve it step by step. In this problem, we are given n items, and each of these items belongs to a group identified by integers from 0 to m1. Some items may not belong to any group, and in such cases, they are assigned a group ID of -1. The task is to sort these items while respecting two key constraints. First, the order of items within the same group must follow the given dependencies. Second, the order of items across different groups must also respect these dependencies. If multiple valid solutions exist, we can return any of them. However, if it is not possible to sort the items while meeting these conditions, we return an empty list. The input includes the total number of items, the number of groups, an array indicating the group ID of each item, and a dependency list that specifies which items must appear before others. This forms the foundation of the sorting problem we need to solve. The output of this problem is a list of integers representing the sorted order of the items, or an empty list if sorting is not possible. Let's consider an example to understand this better. In the first example, we have n equals 8 items and m equals 2 groups. The group array specifies the group ID for each item. For instance, item 0 does not belong to any group as it has a group ID of -1, while item 1 belongs to group 0. The before items list specifies dependencies, such as item 6 needing to appear before item 1. Based on these constraints, one valid sorting order is 6, 3, 4, 1, 7, 5, 2, 0. This order respects both the relative order of items within the same groups and the dependencies between items across groups. Breaking down the example further, the items are divided into three groups. Group -1 contains items 0, 6, Group 0 contains items 1, 2, 7, and Group 1 contains items 3, 4, 5. The dependencies dictate the sequence of items. For instance, item 6 must appear before items 1, 3, and 4, while item 3 must appear before item 4. Additionally, item 5 must appear before item 2. By following these constraints, we can achieve the valid sorting order 6, 3, 4, 1, 7, 5, 2, 0. This demonstrates how dependencies within and across groups are respected while sorting the items. In the second example, the setup is similar, but the dependency graph introduces a circular dependency. The groups remain the same as in the previous example: Group -1 with items 0, 6, Group 0 with items 1, 2, 7, and Group 1 with items 3, 4, 5. The dependencies now indicate, for instance, that item 6 must appear before items 1, 3, and 4, and that item 3 must appear before item 4. However, item 4 also has a dependency indicating it must appear before item 6, creating a cycle between items 6, 3, and 4. This circular dependency makes it impossible to sort the items, so the output is an empty list. Circular dependencies are a key edge case to watch for in this problem. The problem also provides constraints and edge cases to consider. For instance, if there are no dependencies, any topological order of the items is valid. If there are no groups and all items have a group ID of -1, the sorting depends solely on the dependencies provided. Circular dependencies, as we just saw, make sorting impossible, and the output should be an empty list. Lastly, items without groups should still respect any dependencies they are part of but are treated as individual groups during the sorting process. These constraints and edge cases emphasize the importance of handling both group-level and item-level dependencies carefully in this problem. To solve the problem of sorting items by groups while respecting dependencies, we must carefully address two distinct types of constraints: intragroup dependencies, which dictate the ordering of items within the same group, and intergroup dependencies, which define the ordering between different groups. The challenge here is to ensure that both these dependency types are respected simultaneously. One initial approach that might come to mind is a brute force method, where all items and groups are treated as part of a single graph, and we attempt to perform a topological sort on the entire graph. However, this approach fails because it doesn't adequately distinguish between the two types of dependencies. As a result, it can lead to solutions that violate group constraints. While the brute force approach has a theoretical time complexity of O, V plus E, where V is the number of items and E is the total number of dependencies, it is ultimately invalid for this problem because it doesn't accurately model the problem's requirements. A more structured approach involves separating the topological sorting for items in groups. The idea here is to build two distinct graphs, one for groups and another for the items within each group. First, we assign unique group IDs to items that don't belong to any group, effectively treating them as their own singleton groups. From there, we construct a group dependency graph where each node represents a group, and edges capture the intergroup dependencies. Separately, we build an item dependency graph to capture the intragroup dependencies between items within the same group. The solution then involves performing a topological sort on the group graph to determine the order of groups, followed by a topological sort within each group to determine the order of items. Finally, we merge these results, arranging the items according to the order dictated by the group-level sorting. This approach is efficient, with a time complexity of O, n plus m plus e, where n is the number of items, m is the number of groups, and e is the total number of dependencies. While this method is correct and efficient, it requires careful graph construction and handling of edge cases, such as cycles within groups or across groups. An optimized strategy builds upon the earlier ideas but simplifies the implementation by combining the graphs for groups and items. Instead of separating the group-level and item-level graphs, we treat items as part of their respective groups and construct a single unified graph. This supergraph represents both groups and items as nodes, with intergroup dependencies modeled as edges between groups and intragroup dependencies as edges between items within the same group. Once the graph is constructed, a single topological sort is performed across the entire graph. From the resulting order, we can directly extract both the group-level and item-level arrangements. This approach has a complexity of O, n plus e, where n is the number of items and e is the total number of dependencies. It is slightly more efficient than the separate sorting approach because it avoids redundant sorting operations, such as sorting groups and items independently. However, implementing this method requires careful attention to edge cases, including cycle detection, to ensure correctness. The simplicity of managing a single graph makes this approach particularly attractive for debugging and implementation. The chosen approach, which uses a combined graph for both groups and items, stands out for several reasons. First, it ensures correctness by respecting both intergroup and intragroup dependencies through a unified topological sort. Second, it is efficient, achieving an optimal time complexity of O, n plus e, which is well suited to the problem's constraints. Third, it simplifies the overall solution by avoiding the need to manage separate graphs for groups and items, reducing implementation complexity and the potential for redundant calculations. While slightly more challenging to implement than the separate sorting approach, its streamlined handling of dependencies makes it easier to debug and maintain. The key insight, or aha moment, in this approach was recognizing that items without a group could be treated as singleton groups. This insight allowed us to simplify the graph construction process and unify the solution under a single topological sort framework, making it both elegant and practical. In this problem, we are tasked with sorting in items, where each item belongs to a group. The goal is to satisfy two types of dependencies. First, we need to ensure that the items within each group follow a specific order, which are the intragroup dependencies. Second, we need to order the groups themselves based on the intergroup dependencies. The approach to solving this problem involves performing topological sorting twice, once to resolve the order within each group and again to resolve the order between groups. To achieve this, we represent both items and groups as graphs and utilize Kahn's algorithm, a breadth-first search-based method for topological sorting, to process these dependencies step by step. The first step in solving the problem is pre-processing and constructing the graphs. We start by parsing the input. Here, we are given n items, indexed from 0 to n1, divided into m groups. Some items may not belong to any group, so for such items, we assign a unique group to ensure all items are accounted for. Dependencies are provided as directed edges, where before I lists the items that must precede item I. Next, we construct two graphs. The item graph represents dependencies between individual items, while the group graph represents dependencies between groups. Alongside these graphs, we maintain two in-degree arrays to track the number of unresolved dependencies for each item and each group. For every dependency, U, V, we add an edge from U to V in the item graph. If U and V belong to different groups, we also add an edge from group U to group V in the group graph. This step ensures that all dependencies are accurately represented in the graphs. Once the graphs are constructed, we proceed to the topological sorting process. First, we perform a topological sort on the group graph using Kahn's algorithm. This involves initializing a queue with all groups that have an indegree of 0, processing these groups, and reducing the indegree of their neighbors. If a cycle exists, that is, not all groups can be processed, the algorithm returns an empty list, indicating that the sorting is not possible. After obtaining a valid order of groups, we move on to sorting the items. For each group in the sorted order, we collect all items belonging to that group and perform a topological sort within the group using the item graph. If a cycle is detected within any group, the algorithm again returns an empty list. Once all groups and items are sorted successfully, we append the items in their respective sorted order to form the final result. This problem is made more manageable by separating the concerns of intragroup and intergroup dependencies. By addressing these dependencies independently and hierarchically, the logic remains clear and organized. Using adjacency lists to represent the graphs allows for efficient traversal and minimizes memory usage. The indegree arrays are essential for tracking nodes with 0 dependencies, enabling us to process them efficiently. Additionally, the use of topological sorting inherently detects cycles. If a cycle exists in either the item graph or the group graph, the sorting process will fail, signaling that the dependencies cannot be resolved. The solution relies on a few key data structures. First, adjacency lists are used for both the item graph and the group graph to efficiently store and traverse dependencies. Second, indegree arrays are maintained to track the number of unresolved dependencies for each node, whether it's an item or a group. Finally, a queue is utilized in Kahn's algorithm to process nodes with 0 indegree. This combination of data structures ensures that the algorithm is both time-efficient and easy to implement, allowing us to systematically resolve dependencies. Now, let's analyze the complexity of this approach. Constructing the item and group graphs takes n plus e, where e is the number of dependencies. The topological sorting process for both items and groups also operates in n plus e, since each node and edge is processed exactly once. Therefore, the total time complexity of the algorithm is n plus e. For space complexity, the adjacency lists and indegree arrays require n plus e, space to store the graphs and track dependencies. Thus, the overall space complexity is also n plus e, making the solution efficient in terms of both time and space. Let's walk through an example to clarify the process. Suppose we have n equals 8 items and m equals 2 groups, with the group assignments represented as group equals -1, 0, 0, 1, 1, 2, 2, -1, and dependencies given as before equals 6, 5, 6, 3, 4. First, we assign unique groups to ungrouped items, resulting in an updated group array, group equals 0, 0, 0, 1, 1, 2, 2, 3. Next, we build the item and group graphs. The item graph becomes 0, 1, 6, 2, 5, 3, 6, 4, 3, 5, 6, 4, 7, and the group graph becomes 0, 2, 1, 2, 2, 3. Performing a topological sort on the group graph yields 0, 1, 2, 3. We then sort the items within each group. Group 0 sorts to 0, 1, 2, group 1 to 4, 3, group 2 to 6, 5, and group 3 to 7. Finally, combining these sorted groups gives the result 0, 1, 2, 4, 3, 6, 5, 7. When working with this problem, it's important to account for edge cases. For instance, if there is a cycle in either the item graph or the group graph, the algorithm should return an empty list since a valid ordering is impossible. Similarly, disconnected nodes must be carefully handled to ensure that all items are processed, even if they belong to isolated components. To optimize further, we can skip the topological sort for standalone groups that have no dependencies, directly adding them to the result. Additionally, using hash maps to dynamically track items within groups can reduce pre-processing overhead and improve efficiency in scenarios with large inputs. Here, we begin by importing the necessary modules, default dict and deque, to help us build graphs and perform topological sorting. Inside the sort items function, the first step is to handle items that don't belong to any group. These are represented with a group ID of -1. For such items, we assign them unique group IDs by incrementing the total group count (EM). This ensures that all items are associated with a group, even if they initially did not belong to one. Next, we initialize the data structures needed for our graph processing. Specifically, we create adjacency lists for both items and groups using defaultDict. These will store the dependencies for each item and group. Additionally, we initialize item_in_degree and group_in_degree arrays to track the number of dependencies or prerequisites for each item and group. Finally, we populate these graphs in in_degree arrays. For each item, we look at its prerequisites from the before items list. If there's an item level dependency, we update the item_graph and increment the item_in_degree of the current item. If the dependency involves different groups, we also update the group_graph and increment the group_in_degree for the group of the current item. This sets the stage for sorting the items in groups based on their dependencies. Once the group level dependencies are fully captured, we continue by defining a helper function for topological sorting. This function takes in a graph, an in_degree array, and the list of nodes to process. It initializes a queue with all nodes that have no incoming dependencies, meaning their in_degree is 0. These nodes can be processed immediately. As we process each node, we append it to the result list and reduce the in_degree of its neighbors in the graph. If a neighbor's in_degree becomes 0, it's added to the queue to be processed next. The function ensures that all nodes in the graph are sorted topologically, provided there are no cycles. If a cycle exists, the function returns an empty list to indicate failure. Now, we use this helper function to perform a topological sort on the groups. We create a list of all group IDs and sort them based on their dependencies using the group_graph and group_in_degree arrays. If the sort fails, meaning the group dependencies form a cycle, we return an empty list since it's impossible to resolve the order. If successful, we move on to sorting items within each group. To do this, we first organize items by their group using the items_by_group dictionary, where each group ID maps to a list of its items. After grouping the items, we proceed to sort the items within each group. Using the earlier topological_sort function, we sort the items for each group based on the item_graph and item_in_degree arrays. If the sort fails for any group, meaning there's a cycle among the items in that group, we return an empty list since it's impossible to determine a valid order. Otherwise, the sorted items for each group are stored in the sorted_items_by_group dictionary. Finally, we combine the sorted items from all groups to form the final result. We traverse the groups in the order determined earlier by the group-level topological sort, appending the sorted items from each group to the result list. This ensures that both the intergroup and intragroup dependencies are respected. The result list, which contains all the items in the correct order, is then returned as the output of the function. This completes the implementation of sorting items by groups while respecting their dependencies. To implement the solution in Java, we start by addressing the items that do not belong to any group. These are indicated by a group ID of -1. For such items, we assign unique group IDs starting from the current number of groups. This ensures that every item is part of a group, which simplifies the dependency management later. Next, we initialize the data structures needed to represent both item-level and group-level dependencies. Specifically, we use adjacency lists to represent the dependency graphs and arrays to keep track of in_degrees for both items and groups. The in_degree arrays will help us during the topological sorting phase to determine which nodes can be processed at any given step. Additionally, we ensure that every item and group has an entry in their respective graphs, even if they currently have no edges, by initializing the maps with empty lists for each node. Now, we proceed to build the dependency graphs for both items and groups. For each item, we examine its dependencies as defined in the before items list. If an item depends on another, we add a directed edge from the prerequisite item to the current item in the item graph and increment the in_degree of the current item. Similarly, if the two items belong to different groups, we establish a dependency between their groups by adding a directed edge in the group graph and incrementing the in_degree of the dependent group. With these graphs constructed, we define a helper function topological sort to handle the sorting process. This function takes a graph, an in_degree array, and a list of nodes as input. It uses a queue to manage nodes with an in-degree of 0, processing them iteratively. As nodes are processed, their neighbors' in-degrees are decrement, and any with a resulting in-degree of 0 are added to the queue. This continues until either all nodes are processed or a cycle is detected, indicated by the result size being smaller than the number of nodes. The topological sorting function checks for cycles by comparing the size of the result to the expected number of nodes. If the sizes do not match, it indicates that a valid ordering is not possible, and we return an empty list. Otherwise, we return the sorted order of nodes. With this function in place, we perform a topological sort on the group graph to determine the order in which groups should be processed. If the group order is invalid, meaning there are cyclic dependencies among groups, we return an empty list as the overall result. Assuming the group order is valid, we next prepare to sort the items within each group. To do this, we organize the items into buckets based on their group IDs, creating a mapping of group IDs to the lists of items they contain. This mapping will allow us to apply the topological sort function to the items of each group independently. For each group in the previously determined group order, we retrieve the list of items belonging to that group and perform a topological sort on them. If the sorting fails for any group, indicating a cycle within the group's items, we return an empty list as the overall result. Otherwise, we store the sorted items for each group in a map. Finally, we construct the overall result by iterating through the sorted group order and appending the sorted items of each group to the result list. This ensures that both group-level and item-level dependencies are respected in the final ordering. Once all groups and their items have been processed, we return the completed result list, which provides the desired ordering of items while adhering to both the given dependencies and the group structure. Here, we start with a basic example where we have 6 items divided into 2 groups. The group array indicates that items 0 and 1 belong to group 0, items 2 and 3 belong to group 1, while items 4 and 5 do not belong to any group, represented by -1. The before items array specifies dependencies where, for instance, item 1 depends on item 0, item 2 depends on item 1, and so on. In the first step, we assign unique group IDs to items without a group, so items 4 and 5 are placed in newly created groups with IDs 2 and 3 respectively. This updates the group array to 0, 0, 1, 1, 2, 3. Next, we initialize the necessary data structures to build our graphs. We have an item_graph and group_graph to represent dependencies, and item_in_degree and group_in_degree arrays to keep track of incoming edges for items in groups respectively. Initially, all graphs are empty, and all in-degrees are set to 0. Now, we build the graphs and calculate the in-degrees based on the dependencies. For example, item 1 depends on item 0, so we add the edge 1-0 at the item level. Similarly, item 2 depends on item 1, which impacts both the item and group levels, so we update both graphs accordingly. Continuing this process for all dependencies, we end up with the following structures: an item_graph where each item points to the next in the dependency chain, and a group_graph that reflects the relationships between groups. The item_in_degree array is updated to 0, 1, 1, 1, 1, 1, indicating that all items except item 0 have one incoming edge. Similarly, the group_in_degree array is 0, 1, 1, 1, showing that groups are also dependent on one another. Next, we topologically sort the groups using the group_graph, resulting in the order 0, 1, 2, 3. After that, we topologically sort the items within each group. For instance, group 0 contains items 0 and 1, which are sorted as 0, 1. The same is done for other groups, leading to sorted items 2, 3, 4 group 1, 4, 4 group 2, and 5, 4 group 3. With the groups and items sorted, the final step is to combine the items according to the sorted group order. Since the groups are ordered as 0, 1, 2, 3, we append the sorted items from each group in this order. This gives us the final result 0, 1, 2, 3, 4, 5. The output matches the expected order where all dependencies are respected. Now, let's look at a different scenario where a cycle exists in the item dependencies. In this example, we have 4 items, all belonging to the same group. The before items array specifies that item 0 depends on item 1 depends on item 2 depends on item 3, and item 3 depends back on item 0, forming a cycle. Since all items are already in the same group, no changes are made to the group array. The graphs are initialized as empty at the start. Next, we build the graphs based on the dependencies. As we process the before items array, we notice that the dependencies form a cycle. Specifically, the item underscore graph ends up as 0, 1, 1, 2, 2, 3, 3, 0, and the item underscore n underscore degree array has all values set to 1, indicating that each item has exactly one incoming edge. When we attempt to perform a topological sort on the items, we find that it's impossible to proceed because there are no nodes with an in-degree of 0 to start the process. This confirms the presence of a cycle, making it impossible to sort the items while respecting the dependencies. As a result, the algorithm returns an empty array as the final output. In our final example, we consider a case with multiple independent groups. Here, we have 5 items, and the group array indicates that items 0 and 1 belong to group 0, items 2 and 3 belong to group 1, and item 4 does not belong to any group. The before items array specifies that item 2 depends on items 0 and 1, and item 3 depends on item 2. First, we assign a new group ID to item 4, which updates the group array to 0, 0, 1, 1, 2. The graphs are then initialized as empty. As we build the graphs, we find that item 2 depends on items 0 and 1, so we add the edges 2-0 and 2-1 to the item underscore graph. Similarly, item 3 depends on item 2, so we add the edge 3-2. This results in an item underscore graph of 0, 1, 2, 0, 1, 3, 2, 4, and an item underscore n underscore degree array of 1, 1, 0, 1, 0. Since there are no group level dependencies, the group underscore graph remains empty. To analyze the time complexity, we start by looking at the individual steps involved in the solution. First, when assigning unique group IDs to items without a group, we iterate through all n items exactly once. This operation is straightforward and takes n time. Next, we construct graphs for items in groups. For the item level graph, we iterate through all the dependencies listed in before items. If the total number of dependencies is denoted as e underscore items, this step requires e underscore items time. Similarly, for group level dependencies, we check if 2 items belong to different groups for each dependency, which also takes at most e underscore items. Combining these, the graph building process takes e underscore items overall. Then, for the topological sort of groups, we process all m groups and their edges. If the total number of group level dependencies is e underscore groups, the topological sort for groups takes m plus e underscore groups. Each of these steps contributes to the overall time complexity, and we'll continue evaluating the remaining steps in this process next. Now, considering the topological sort for items within groups, we need to process the items for each group individually. Since there are n items in total and the dependencies among them remain e underscore items, the topological sorting of items across all groups takes n plus e underscore items. After that, we combine the results by iterating through the m groups and assembling their associated items in sorted order. This combination process involves a simple linear iteration through the groups and their items, requiring n time. When we look at the overall time complexity, the dominating phases are graph construction and topological sorting. Item-level operations involve terms like n plus e underscore items, and group-level operations add m plus e underscore groups. In the worst-case scenario, where every item depends on every other item, e underscore items could reach n squared. Similarly, e underscore groups could be as large as m squared if every group depends on every other group. Combining these terms gives us a worst-case time complexity of n plus n squared plus m squared, which simplifies to n squared plus m squared. Let's now analyze the space complexity step by step. First, we consider the storage required for graphs. The item underscore graph adjacency list stores dependencies between items, which takes e underscore items space, while the group underscore graph adjacency list stores dependencies between groups, requiring e underscore groups space. Next, the in-degree arrays for items and groups contribute to space usage. The item underscore n underscore degree array needs n space since it stores the in-degree for each item, and the group underscore n underscore degree array requires m space for storing the in-degree of each group. During the topological sort process, we use a queue that can hold at most all n items or all m groups at a time, which means the queue requires O, max, n, m, space. Additionally, there are intermediate data structures like the items_by_group dictionary, which organizes items by their group IDs, and the sorted_items_by_group dictionary, which stores sorted items for each group. Both of these dictionaries require O, n, space. Finally, the result list, which stores the final sorted order of all items, accounts for another O, n, space. These individual components collectively contribute to the overall space complexity. When we summarize the overall space complexity, the dominating terms arise from graph storage and the intermediate results. Specifically, the graphs for items in groups require O_items plus E_groups space, while arrays and intermediate data structures like items_by_group and sorted_items_by_group contribute O, n plus m, space. In the worst case, where E_items equals O, n squared, and E_groups equals O, m squared, the overall space complexity becomes O, n squared plus m squared. Comparing this optimized approach to a brute force solution highlights the efficiency of our method. A brute force approach, which would involve trying all possible permutations of items and verifying dependencies for each, would take O, n *k, where k is the time required to verify dependencies. This is computationally infeasible for large N. In contrast, our graph-based approach with topological sorting reduces the complexity to O, n squared plus m squared in the worst case. Moreover, in the best-case scenario with no dependencies, the solution is linear, O, n plus m. For sparse dependencies, the average case complexity tends to be closer to O, n plus m, while fully connected dependencies lead to the worst-case complexity of O, n squared plus m squared. The mathematical justification for these complexity results lies in the structure of the problem. The dominating terms, both in time and space complexity, stem from the processes of graph construction and topological sorting. Since the problem separates item-level and group-level dependencies, the overall complexity is the sum of the complexities for these two layers, O, n squared, for items and O, m squared, for groups. By leveraging this separation, the solution optimally handles the dependencies while ensuring that the complexities remain additive. This approach is not only efficient but also adheres to the constraints of the problem, providing a scalable solution for large inputs. One of the most common mistakes in this problem is failing to distinguish between intragroup and intergroup dependencies. Intragroup dependencies refer to the ordering of items within the same group, while intergroup dependencies define the relationships between different groups. Treating all dependencies as if they belong to a single graph often leads to incorrect topological orderings because it ignores this hierarchical structure. Another frequent issue is errors during graph construction. For example, mapping items to their groups incorrectly or failing to account for items with no group, where group I equals -1. Such mistakes can result in invalid topological orders or even runtime errors. Additionally, many assume that the dependency graph is fully connected, which is not always the case. Disconnected components are common in this problem, and neglecting them can lead to incomplete results. Finally, improper cycle detection is another critical pitfall. Cycles in the graph make it impossible to determine a valid ordering, so your algorithm must handle these cases gracefully by returning an empty list whenever a cycle is detected. Inefficient graph traversal is another area where mistakes are often made. Using naive DFS or BFS strategies without leveraging adjacency lists or in-degree counts can significantly increase the time complexity of your solution, especially for large inputs where n and m can go up to 10 to the power of 4. To solve this problem efficiently, you need to think of it as two topological sorts, one for determining the order of groups and another for sorting items within each group. This decomposition is the key insight for solving the problem effectively. It's also helpful to recognize that this is a classic dependency resolution challenge, similar to what you'd find in build systems that resolve package dependencies. During interviews, you should be ready to explain why two levels of topological sorting are needed and how your solution handles cycle detection. Additionally, highlight your use of adjacency lists and in-degree arrays, which enable you to achieve an efficient O, n plus m, complexity for topological sorting. This problem is closely related to several other LeetCode problems that also involve graph-based dependency resolution. For instance, LeetCode 207, Course Schedule, focuses on detecting cycles in a dependency graph to determine if a valid ordering is possible. Building on that, LeetCode 210, Course Schedule 2, extends the challenge by requiring you to return the valid topological order. Another related problem is LeetCode 444, Sequence Reconstruction, where the goal is to reconstruct a sequence from given subsequences. This emphasizes the importance of graph construction and topological sorting. Finally, LeetCode 269, Alien Dictionary, is a variation of topological sorting where you need to determine the order of characters in an alien language based on given word dependencies. These problems share similar techniques and concepts, so practicing them can help solidify your understanding of topological sorting and graph-based problem solving. To solve this problem, there are several alternative approaches you can consider. One option is using a DFS-based topological sort. While DFS is memory efficient, it can be less intuitive for handling two levels of dependencies, such as those between groups and within groups. Additionally, cycle detection can be more challenging to implement correctly with DFS. A more common approach is Kahn's algorithm, which uses BFS for topological sorting. This method is often preferred because it is straightforward to implement and manages in-degree counts efficiently. The trade-off here is that it requires additional space for the queue, but this is usually negligible compared to the clarity it provides. Another technique involves union find for pre-processing groups. While union find can be helpful for merging groups, it is less applicable when strict ordering between groups or items is required. Each of these approaches has its trade-offs, so selecting the best one depends on the specific requirements and constraints of the problem. Great job! In summary, we tackled LeetCode problem number 1203 using graph-based algorithms and topological sorting to manage dependencies. Remember, breaking down problems into smaller parts is key to solving complex challenges. Thanks for tuning in. Don't forget to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!